I'd like to welcome everyone to this meeting. I have a few notes here I wanted to remind everybody before we kick off the meeting. So our monthly meeting is scheduled for the second Tuesday of each month. Please check out our website for more information. And do not forget to check out the newsletter from Yvonne. There's a lot of information in there and a lot of updates for the past event and also for the future event. And a reminder for the upcoming No Magic Symposium in Allen. So we gave out all of the vouchers, but if you still wanted to go, please contact Yvonne, myself, or Barry. Now I'd like to introduce Yvonne to introduce our guest speaker.
Hi. So tonight we have Kelly DeFazio. She is the F-35 Director of Production Engineering. Kelly is responsible for manufacturing, testing, and planning, and she also does root cause and analysis and corrective action of the production sites. She has been the site director for Cortland at Space Systems, and she's been responsible for procurement through the assembly, integration, and test team, and also for delivery of missile systems. And she has also managed and maintained a 660-plus acre ordnance-rated facility with over 125,000 square foot of production floor space. Kelly is a certified professional engineer, awesome by the way, and she has a degree in electrical engineering and a master's degree in business administration from the University of Central Florida. Thank you for coming, Kelly.
All right, thanks, Yvonne. So I have to thank Lon for asking me to do this presentation because it's been fun for me just putting the information together, and I hope you guys enjoy it tonight. I didn't know what to talk about. He was encouraging me to talk about lessons learned from a systems engineering perspective because when I graduated from UC in Orlando with my EE degree, I joined Marietta Astronautics at the time at the Cape as a systems engineer, which I guess I didn't realize until I was doing the study for this presentation that it was kind of in its infancy at the time from a field perspective and a discipline perspective. So we're going to do a little bit of a history lesson tonight on engineering in general, systems engineering, and also the lessons learned that I've had through my experience as a systems engineer as well as program manager. And then I have a call to action for you all. So, I do have some questions for you, so hopefully it'll be a little bit of a dialogue. And I know you uploaded the file, so if there's anybody online, don't look ahead and don't look at my notes because the answers are in the file. But, so I have to say, life without systems engineering, is that an option? So by the end of this presentation, we'll be able to answer that. So, what was the first documented form of engineering? What would you say is what's the first thing that comes to mind when you think of what's that first inventive thing that happened in the history of time? What would you say it is?
Are we sharing slides?
And you think of the wheel and you think of transportation, but actually the early wheel was created for pottery. It was the potter's wheel. And we're talking 4 or 3000 BC. So this is one of the early mechanical engineering inventions, according to Wikipedia. And oh my goodness, Wikipedia online is incredible. The kids in school today have it made, let me tell you, online searching. So who's the first documented engineer, you think?
Ooh, very good questions.
Go way back.
Greek,
It is, I'll give you, it's Egypt. Egypt. All right.
Now that was Martian.
So, the character name, I believe you pronounce it Imhotep.
I was never going to guess.
I think it's Imhotep, maybe there's a better way to pronounce it. 27th century BC. The first documented Egyptian polymath, scientist, architect, he was a physician, and there's an image, I guess, of his likeness that is a statue that is in the Louvre in Paris, but he was the engineer and architect that created the pyramid for his king Zoser back in the 27th century BC. And Hollywood gets in on the act, and you guys might remember this. That was the character in the 1932 film The Mummy. So that was actually Imhotep. He came back as the mummy in the film. All this you can find out on Wikipedia.
I think he's in the new movie too.
They do, yes. They bring him back a couple of times. It's amazing. But that was Boris Karloff. That was his image. So I've seen that image now for 2 weeks. I now I dream about it now. All right, so who made this statement? I think I actually remember this from college. Give me a lever long enough and a fulcrum on which to place it, and I shall move the world. And some consider the person that made this statement the father of engineering.
We're going to go Archimedes.
Archimedes? Archimedes. Oh, wow. 278 BC, the father of engineering, some credit him as that. He did several things. He was a great mathematician, physicist, engineer. He anticipated calculus. He was commissioned to build a very large ship, the Syracusia, I guess, and it carried 600 people, not only for luxury, but it was also used in war. And he created the Archimedes screw, which, because the ship leaked quite a bit, had to get rid of some water. So that was one of the early mechanical devices as well.
We have a image of the Archimedes screw at Flitterbond.
At where?
At Flitterbond, at the water park.
Oh, oh yeah. Yeah. So, anyway, still, no sign of systems engineering, but I keep looking. I'm searching. So, get into the Renaissance era, and when I continue to search on key engineering folks and inventions and monuments and milestones, Leonardo da Vinci comes in, and I was kind of surprised about that, but they talk about, of course, his, let's just say, his foresight and his technical ingenuity with the flying machines, the drawings. He even, I guess, conceptualized an adding machine, solar machines, armored fighting vehicles, along with, of course, his artwork. So some would consider him one of the fathers of engineering in the Renaissance era. Thomas Savery, the mechanical engineering, was T. Do you guys know Thomas Savery? Now, I was surprised to find out this, but he was the first one. Now, we're talking 1650, 1715 was his date of birth and death, but he was the first one to create the first steam engine, and I was remembering a different name for the steam engine, which was actually later. This was the early version of the steam engine.
Whose name were you remembering for the steam engine?
And now that you say that, wait. Somebody else? Yeah, look at it on Wikipedia. And of course, you know, the steam engine several decades later gets into the Industrial Revolution and mass production. So any other names come to mind for key engineers that I might have on this chart? Key fields of engineering, key players in the Renaissance and leading into the modern era?
Clark Maxwell comes to mind.
Clark Maxwell, yeah.
Hadron, but he was more of a civil engineer.
Yeah. There's a lot. There's a lot that popped in. John Smeaton, he was English.
The Bolton and Watt, the 1870s, 1817, is that?
Yeah, the Bolton and Watt engines. Yeah, that was a different type of engine. There's a lot. There's a lot of different types of engines. Smeaton he was English, and he did bridges, he did lighthouses, harbors, canals, And then we get into the electrical
Oh,
age.
sure, it's a Spanish name, which I will attempt to say, from 1608. I'll let you do this. The Spanish inventor obtained the first patent for the steam engine in 1606. And then in 1690,
Yeah, I can't.
Thomas Avery.
Yeah, I cannot pronounce that.
His name is
I
Geronimo, and his last name is Beaumont, and there's some Spanish stuff in between. I don't do Spanish, sorry. English is my only language.
I actually can do Volta, so, marrying an Italian, so I can, I wasn't sure about one of the other names, but I can say Alessandro Giuseppe Antonio Anastasio Volta.
New
So I can say that.
1712.
So Volta was the inventor of the electric battery. So he was a physicist and a chemist that started and pioneered the electricity and power generation. And then another key player in electrical engineering was Faraday. And Faraday, of course, came up with the basis and established the electromagnetic field and the beginning of the insertion of electronics with technology, inserting electronics and electricity into technology. So key building blocks in the world of engineering, but still no systems engineering, and we're all the way to 1867. Did you guys know when systems engineering started? Formally? 60s?
Yeah.
Close. Close. So the first that I could find was Bell Labs in 1940. So the Bell Labs in 1940 was the first to use that phrase, and we'll talk about that as a little bit of a case study in a moment. But in addition to Bell Labs, in the late 40s, the Department of Defense, and specifically the missile defense industry and getting into ICBM-type technology, missile technology, the systems engineering approach really started to take hold. And then NASA and the space program really did formalize systems engineering along with MIT and academia in the 50s and going into the 60s. Key player, Simon Ramo, I'm not sure if it was Ramo or Ramos. Anybody know this person? This was amazing. Like I said, doing this little presentation, I was just amazed. I found out so much I didn't know about this industry. So Ramo was, as you see, he just passed away last year for one thing. He was 103. And some would consider him the father of systems engineering and even the father of ICBM technology. He started a couple of companies that actually started under his name that turned into TRW and that turned into a portion of Honeywell. He had, I believe it said, 50 patents by the time he was 30. So he was quite an entrepreneur. He also developed microwave, missile technology, I mentioned that, and I believe there was one other.
I thought the microwave was Marconi.
It said microwave, but I didn't know what piece of that technology.
Okay.
So I think it might have been a piece of the technology, not the actual microwave itself.
Okay.
So, yeah. And the other thing I noticed about Wikipedia is I'm not sure how accurate every bit of that information is. Yeah.
Reliable source.
Yeah. You can write in and tell them whether they're right or wrong, and I thought, okay, that's an interesting thing.
Academia.
Yeah. So, but he was definitely a key contributor to engineering in general. So what about systems engineering in general? Is there a key person in your mind that comes to mind for systems engineering? I mean, certainly it's an emerging field, really. I mean, we're in the middle of it. When I went to school, that was not an offering. Like I said, I graduated as an electrical engineer, hired into the company as a systems engineer, even though I wasn't quite sure what that was. But we'll talk about what my job was in a minute. was a key player in systems engineering as well. He worked, he got his PE degree and control engineering degree, and he worked on the Apollo program. He was actually more on the academic side. He was an author. But this was in one of his books. This was his definition for systems engineering tools, and that might have been the name of one of his books that he wrote in 1965. And I thought this is a pretty good definition of what systems engineering is all about. He says the method seeks to optimize the overall system functions according to the weighted objectives and to achieve maximum compatibility of its parts. So it's really looking at achieving and maximizing the requirements of the whole system, by using individual pieces and parts, and not just maximizing the pieces and parts, but maximizing the whole. And I thought that was a good way to define the process. So, talking about Bell, going back to the 1940s, what I found there's really two consistent reasons for systems engineering in the emergence of it. One is a business reason, the business perspective. Systems engineer, Bell, they were in the telecommunications. They had a geographical, complex situation where they wanted to take their technology, they wanted to take their service and take it worldwide. So they had to figure a way to standardize their tools, standardize their techniques for their suppliers, their raw materials, their training, their installation, their sales, and everything. So they used that process to be able to deploy their system in a cost-effective, efficient way to make money. So, that's what drove their needs. So their complexity was one of geography to maximize their profits. And, of course, they used a pretty straightforward model to design their system around that, to standardize, as I mentioned, their raw materials, their interfacing, and to kind of drive every application to a standard approach. And I think some of you might remember, but we actually got your phones from Small Bell at one time, and you actually if you wanted to use a different phone, I think you even had to pay rent or something for a different phone or something.
Yes, you didn't own your phone.
So yeah, it was quite a monopoly. Very different from today. So then NASA comes along, and the complexity is not just a business need; it's really truly a technical, complex situation. One of the things, of course, that drives the need is that driving force and that move, and of course our race to the moon really provided the catalyst to push the team. So I always resonated, growing up on the Space Coast in Florida, I always resonated with the Kennedy speech where he says, we choose to go to the moon not because it's easy, but because it's hard. So I wanted to play that here for you tonight.
William Bradford, speaking in 1630 of the founding of the Plymouth Bay Colony, said that all great and honorable actions are accompanied with great difficulty, and both must be enterprised and overcome with answerable courage. If this capital history of our progress teaches us anything, it is that man in his quest for knowledge and progress is determined and cannot be deterred. The exploration of space will go ahead. Whether we join in it or not, we mean to be a part of it. We mean to lead it. For the eyes of the world now look into space, to the moon, and to the planets beyond. Our leadership in science and industry, our hopes for peace and security, our obligations to ourselves as well as others, all require us to make this effort, to solve these mysteries, to solve them for the good of all men. There is no strife, no prejudice, no national conflict in outer space as yet. Its hazards are hostile to us all. Its conquest deserves the best of all mankind. We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other thing. not because they are easy, but because they are hard. Because that challenge is one that we're willing to accept, one we are unwilling to postpone, and one we intend to win.
Nothing like a good challenge with a deadline to get you motivated, right? So it gives me chills. So that's good. So you've got the makings of the perfect reason to really define the systems engineering approach. The difficulty of sending a man to the moon in that hostile environment, coupled with the goal and the commitment of doing it within the decade, of course, to beat the Russians to it, right? And of course, they were on orbit before we were, but we got to the moon first. If you believe that. Some people think we just went to Hawaii, but that's a whole other story. So I will, that'll be for another night long. We'll have another talk on that. So my parents left Pennsylvania and went down to the Space Coast in 1958 to be a part of the space program. So I grew up watching Saturn's launch, and it was a pretty cool environment to grow up. But I didn't really realize that NASA and missile technology in space was really the catalyst that really started forming this discipline. I found in the NASA Systems Engineering Handbook that I guess was published in '95 a definition that talks to systems engineering being a robust approach to the design, creation, and operation of systems. And in simple terms, the approach consists of identification and quantification of system goals, creation of alternative system design concepts, performance of design trades, selection and implementation of the best design, verification that the design is properly built and integrated, and post-implementation assessment of how well the system meets or met the goals. So it talks about the entire life cycle of the program. And so often, it took me back to so often, even today, program managers choose to use systems engineering as their discretionary fund, I'm afraid. And when they get in trouble with cost, they go, okay, let's see, I finished the SRR, my requirements are defined, I got through the PDR, got, halfway through my months to get to critical design review, I'm kind of running out of money, okay, get rid of 50% of the systems engineers. But what's so critical, and I'll talk about that more when I get to my lesson learned, is, and as NASA points out, systems engineering is about the entire life cycle and validating that you have met the total system requirements until you get to the end. You don't know that you've arrived, and so we got to make sure we close the loop. But anyway, so back to the space mission to the moon. So there were 4 possible mission modes of how we would get to the moon. So it's a classic case, so a technical case to be solved, but in addition to that, it's a government program. There's 500 contractors. And from 1960 to 1965, there grows to over 300,000 procurement actions. And there's over 250 subcontractors, and, of course, millions and millions of parts and components that need to meet specs and requirements. So with all of that complexity, making sure that the interfaces, of course, line up, and systems engineering defined approach is the only way to operate that kind of complexity from a business perspective. Just as gee-whizzing curiosity, I thought I'd put the first 5 prime contractors up here: Boeing, Douglas Aircraft, Northrop American Aviation, Rocketdyne, and IBM were the first 5 prime contractors on the Apollo program. So the 4 options to go to the moon and back, the first 2 consisted of direct ascent and the Earth orbit rendezvous. And that artist rendering on the right-hand side is what those first two options would have looked like had they been chosen. but NASA had 4 options to go take a look at and do the risk trades and the cost trades and the technology trades. And in the early 60s, 60, 61, these 2 options were the first 2 that NASA was leaning towards. It was their preferred option. The direct ascent vehicle here shown on the right is about 3 or 4 times the size taller than what we actually use with the lunar module version. So much heavier, much larger, and in fact, if you just look at the direct ascent option 1, this would have been a part of the whole stack, the launch vehicle, and it would have been essentially launched, separated and ignited from the launch vehicle and land on the moon, and then it would have left its landing stage on the moon, left the moon, and gone all the way back to Earth. So that's the way that would have worked. The problem with that is it's extremely heavy, and the Saturn could not have lifted that. They would have had to the Saturn V would not have lifted that. They would have actually had to make a bigger launch vehicle, and I guess they were going to call it the Nova. And I just can't imagine. I could have looked it up. I didn't see how big that was, but the Saturn V is huge. So the Nova would have been just enormous. The Earth Orbit Rendezvous was a similar approach. However, it was kind of an international space station kind of thing where same rocket configuration going to the moon, but instead of launching that on the Nova larger launch vehicle straight from Earth, they would have launched several rockets in pieces and actually assembled that in Earth orbit like they assembled the International Space Station, and then it would have gone to the moon, and then a piece would have come back. The problem with that is they speculated there would have been about 15 additional launches to get all those pieces into Earth orbit and assemble it, so a lot of extra cost there. But still, those were the 2 favored approaches in the beginning by NASA. So the third option, the Lunar Orbit Rendezvous, is you all should recognize the lunar module to the right is the option that was selected, and that of course is a much lighter weight version. This module was launched as part of the Saturn V. It separated and landed on the lunar surface. When they were done, of course, only 2 astronauts. 1 would remain up in the lunar orbit. 2 would get in the lunar module, go to the surface, and then they would crawl into a portion of that spacecraft, eject from the lunar module, and go back to the command module, and they would dock to the command module and go back. The reason that NASA didn't like this approach, they felt like it was high risk because they had never done the docking maneuver before. They had never done it, certainly never did it in lunar orbit, and they never even did it in Earth orbit. So it was a very high risk approach, and so a lot of them didn't like it. The Lunar Surface Rendezvous, the 4th option there, was essentially 2 separate launches. One was kind of a gas station. It would launch first, it would go straight to the moon with propellant, and wait for the second launch, which carried the astronauts. And once they got to the moon, they would do a propellant transfer and come back. So that was the 4th option. Doesn't sound too awful unreasonable, but that didn't seem to carry much weight, I guess, in their approach. So, again, so the first 2 options were favored. The engineers feared the docking risk. John Fugel at Langley, he was key to the decision-making process. He really kept pushing for the lunar module option, the LOR option, and he actually went over the hierarchy in NASA and really wanted them to keep looking at that. Like, look, you really got to keep looking at this. This is really an option that should not be taken lightly. So he wrote a lot of letters to the NASA Associate Administrator and kept pushing for that. Robert Siemens was his name at the time, the associate administrator. And they were listening, but they really didn't get into it too much. But back to the systems engineering approach. So the administrator said, well, I'm going to establish this ad hoc team, and I need them to recommend a launch vehicle. So go back to, the requirements of the whole system, drives a need for the piece parts, right? So by creating the ad hoc team and just saying, look, you got to tell me which launch vehicle we're going to use. And of course, through the whole process, they said, well, the launch vehicle obviously drives the mission mode decision, and the team came back and said, we recommend the LOR or the EOR as a hybrid. But the team came back and kind of surprised them and said, well, John's kind of right. The LOR is what you need, and we're recommending the Saturn V. So that went on for a little while. The people at Marshall Space Flight Center didn't like that decision for many reasons. Part of it was probably their employment. They probably liked the idea of making a big new Nova launch vehicle. I would guess. But Von Braun made the decision and made the announcement in '62 that they were going with the LOR. But the whole process was the evaluation of the system as a whole, weighing the risk, what are the options, classic case of systems engineering. So the LOR, one of the benefits is somebody pointed out, hey, the LEM could be a lifeboat, just in case there's a problem with the command module. Just saying, right? And in the documentation, they said, well, that's fine, but there's no single reasonable command module failure that was identified that would cause a service propulsion system problem. So I hear you, and it can be a lifeboat and all, but there's no single point of failure that's going to be a problem. But I think we've all seen the movie, and we all know history. If you haven't seen the movie, you need to watch Apollo 13.
So you're telling me you can only give our guys 45 hours? That brings them to about there. Gentlemen, that's not acceptable. You gotta talk about power here. Whoa, guys! Power is everything. Power is everything. Without it, they don't talk to us, they don't correct their trajectory, they don't turn the heat shield around. We gotta turn everything off. Now. They're not gonna make it to re-entry. What do you mean everything? With everything on, the LEM draws 60 amps. At that rate, in 16 hours, the batteries are dead, not 45. So's the crew. We got to get them down to 12 amps. 12 amps? How many? You can't run a vacuum cleaner on 12 amps, John. We got to turn off. We have to turn off the radars, cabin heater, instrument displays, the guidance computer, the whole smack.
Whoa, guidance computer. Well, what if they need to do another burn? Gene, they won't even know which way they're pointed.
The more time we talk down here, the more juice they waste up there. I've been looking at the data for the past hour.
That's the deal?
That's the deal.
Okay, John. And then we finish the burn, we'll power down the LEM. Now, in the meantime, we're going to have a frozen command module up there. In a couple of days, we're going to have to power it up, use nothing but the re-entry battery.
We've been tried before. No, we've never even simulated it before, Gene.
Well, we're going to have to figure it out. I want people in our simulators, working re-entry scenarios. I want you guys to find every engineer who designed every switch, every circuit, every transistor, and every light bulb that's up there. Then I want you to talk to the guy in the assembly line who actually built the thing. Find out how to squeeze every amp out of both of these goddamn machines. I want this mark all the way back to Earth with time to spare. We never lost an American in space. We're sure as hell not going to lose one on my watch. Failure is not...
So this takes me to a couple of my personal experiences, and I'll have to tell you though, so my dad was, as I mentioned, with the space program, and he actually was part of the Grumman team, and it was, interesting to think about how he played a role in those activities as well. So this particular launch complex you see here, Complex 41, has the Titan Centaur sitting on the launch complex, and this is our mobile service tower. And this white building just off to the side, down on the ground level here, behind the Titan, is the HVAC control center. And that's going to be the setting of my lessons learned story as a systems engineer. But before I leave the Apollo 13 story completely, I'll have to say Gene Krantz, the launch director there, as I left the cave at the end of the Titan program, I had the pleasure to be a launch conductor for the Titan program, and which is basically what his role was, and that is just one of the best memories ever. And if you ever watched the movie, he put on that new vest, and every launch he had a new vest and a patch, and I didn't even realize it, but it became a tradition. People in the space industry are very superstitious, And, I didn't realize that until I started working there, but the first launch that I was a launch conductor, I just thought it was special, and so, I bought a new suit. And so sitting as a launch conductor, I had my new suit on, and of course everything went well, and we launched the rocket. And so that day, and everybody's, cheering and shaking hands, and they said, you realize every time you sit as a launch conductor now, you're going to have to buy a new suit. And of course, I'm like, okay, I don't have a problem with that. I will do that. But why? What's the deal? And they're like, because you got to do everything went good. Now you got to do the same thing every time. So everybody had all these little traditions. They're very superstitious. It's very strange. So as I was hired as a systems engineer, my job when I was hired in was to as the programmable aerospace control equipment PACE was our ground computer, and I was a systems engineer, and I was in charge of making sure that our ground computer, which was in this white building off to the right of the rocket here, which is where our ground computer was, goes up through the umbilicals and interfaces with the vehicle, and out throughout the entire flow, that computer system would check out and make sure the rocket was operating the way it needed to be. So as the PACE systems engineer, I would make sure that all of the subsystem level testing was good, all the data looked good, and on launch day, then I was given the opportunity to sit on console and make sure that the data was good and give one of the final goes for launch. So that was my day job. Well, in this particular scenario, my lessons learned for why systems engineering is important, they said, well, you know what? You just graduated. You must know something about software and computers. It was 1988, right? 1889. And most of the folks out there had been there for 20, 30 years. And I mean, we had backstations, right? I mean, that's what we had. And so we just activated the complex, the launch complex, with all new equipment. And part of what was in that building was a new HVAC control system, completely redundant and completely automated with PLCs. And the PLC was programmable logic controller, which is based on PID loop controllers. This particular one was a triplex version, and so the controls was triplicated, the hardware was duplicate, redundant, and it fed the air conditioning system that went up to the payload, the upper stage Centaur, and the vehicle itself, the launch vehicle. One of the things that we needed to do as part of the Centaur requirement, the Titan Centaur, is this upper stage is a cryogenic upper stage. It has the LH2, the liquid hydrogen, and the LOX, which is super cold. And in addition, we had these thermal blankets on there. And because the propellant is super cold, it has a very low boil-off point. So what the thermal blankets were for is when you're in orbit, you don't want your solar heating to create a warm environment for that propellant because it would boil off. And of course, once you boil off your propellant, then you have no thrust. So it was very important to keep these thermal blankets, and it's the same way today, we still enter upper stage, to keep those thermal blankets in their optimum condition. So on launch day, what we would do, and you can't see it off to the left of the launch pad here, but the umbilicals are coming up the tower and they come on the back side of the aircraft. But what we would do at T-minus 4 hours, we would, before T-minus 4 hours, we'd clear the launch pad of everybody. Everybody would fall back about 4 miles to our control center. And we would switch from our automatic station. We would switch the air conditioning system from air over to gaseous nitrogen. So we would switch the air, and it would gradually, it was intended to gradually switch from air to nitrogen so that we took the atmosphere that was up in the payload fairing, around the Centaur, and in the beginning, even at the 2A compartment, from a somewhat moist environment to a very, very, very dry environment, because when we started loading cryos and making the Centaur very cold, we did not want any moisture to condense on the thermal blanket. Because if moisture condensed on the thermal blankets in orbit, going through orbit, they would freeze, and if the blankets froze, had ice on it, then the properties of the blankets would be degraded, and they could not keep the propellants in the condition that they needed, and the Centaur would not operate. So, very complex system, on-orbit requirements, systems engineering approach, driving it all the way back down to an HVAC control system. So, keep in mind, I'm hired to go worry about launching a launch vehicle because I was hired in '88 and got a degree in, the late '80s, and I knew something about software. I think I had one class in Fortran. And they said, oh, okay, so we had to, typical, program decision, we weren't going to launch the Centaur till way later because of other reasons that drove the Centaur mission late. The A&E firm that designed the HVAC system had activated everything with the HVAC system except for this function of transitioning from air to nitrogen. And, the program managers wanted to finish the contract and get the A&E firm out of there. Get everybody out of there, start launching the regular Titans, and we'll worry about the Centaur version later. So we got rid of all the designers, all the activation, all the A&E people, get rid of them. And so now it's, 1989, and they said, Kelly Webster, that was my maiden name. A guy by the name of Dan DeFazio, that's my now husband, and a couple other, he was electrical, a couple mechanical engineers. They said, okay, you four, go activate that system. So the deal is we had to hold tight requirements up here. So our sensors were way up here at the entrance to the launch vehicle. They had to go down the tower, we're talking 200 feet, down the tower, and out the back of the launch tower into the HVAC system. We had to drop the humidity. Gaseous nitrogen naturally does, dry. So drop the humidity to 0, your dew point goes negative. We had to maintain temperature. Cleanliness requirements, you're in a clean room, you got a satellite, you got sensors, you got mirrors, you got all that good stuff. So we have to keep positive pressure. So as we are dropping the air and raising the nitrogen, we could not drop the pressure inside inside the launch vehicle or the fairing, because the air we were pumping in was like 5,000 clean, and the air in the UES environment was 100,000 clean. So you wanted to keep positive pressure on the inside. So as we're transitioning these huge dampers on the air conditioning system, we couldn't drop the pressure up at the top here, because then we would contaminate the satellite. So anyway, a lot of complex requirements. So we use the programmable logic controller, the PLC, to do this. I got a quick lesson in PID theory. Anybody ever done PIDs, PLCs, logic controllers? Yeah.
Not that particular controller, but other controls.
Yeah. So essentially, the way it works, we actually use quite a bit. We have several on the plant here, I'm sure, and others on the phone. I'm sure they have them on their plants. GE Fanuc, I think, is a very common PLC these days. You're controlling a process variable out here on the right. You have a set point, and then you've got a feedback loop across the bottom. You can barely see it here. And you're measuring an error, and based on that error, you add either a proportional, an integral, or derivative component of a process, whether it's temperature, you're modulating temperature, humidity, whatever it is you're controlling, you're adding a little bit of that variable to control your output. So you either add gain, straight gain on the left, the middle is an integral, and the right is a derivative. So if what you're seeing here is the gain is pure amplitude on the left, the middle is more of a response time, so you feel oscillation that changes over making it faster or slower, and then the derivative kind of dampens it out. So let me go to the next chart and puts it all together. So we're tuning these loops to try to make this system work smooth as we transition the air conditioning system. And we're doing this night after night after night, and there's tons of these PIDs changing pressure release valves, pressure control valves, heating coils, everything, because we had to warm up the nitrogen, because nitrogen is actually very cold, too. So we're warming it up because we need to keep the temperature warm. So we're doing this for 2 months, and we couldn't get it to work. The system was not behaving. And we just tried night after night. We even took turns sleeping in the van out of the lunch complex, just taking turns sleeping night after night. So we're pretty sleep deprived at this point. And here's a very, very, very simplified look at the system. So basically we have 5 air handling units. Here on the right-hand side is a launch stack. Like I said, if you go all the way to the top, it's in this configuration, it's about 200 feet. But basically on the left-hand side, we had a 5,500 PSI cross-country nitrogen line that came across the case. Came at pretty high pressure in the pipe. And we had a 3-stage pressure regulation system that would bring it down to 100 inches of water column. So we're talking a couple PSI, right? Pretty big drop. They would feed through each air handling unit, and then we condition it with the heat and go back up the tower. So we're trying to make all these valves up and down to behave with each other, and they just weren't behaving. And doggone those pressure relief valves, right when we got it just about where it was going to get under control, the relief valves would pop off and everything would go crazy again. So one of the 4 of us, and I told my husband I wouldn't tell on him, but it was him. And he said that, let's look at the data. Data's going to drive it all. So we looked at the data, and we were seeing the relief valves were popping off. Well, here's a lesson learned, too. The relief valves were controllable. And you probably should not put controllable relief valves in the system because engineers are going to try to control them, right? So we decided, let's just hold the top down just a little bit, so that if it pops, it doesn't pop all the way, just a little bit. So we did that. And the system started to behave a little bit better. I'm like, oh, that works pretty good. Well, but it's still not operating the way it needs to, but that was a step in the right direction. So, but we still we're kind of playing with fire, but we're sleep deprived, and we got a deadline. Not quite Kennedy's deadline, but we got a deadline. And so we tried a little bit more, and until we blew up an air handling unit pipe. It found its weakest link, and it was a manual damp valve. We heard this huge explosion right outside the control shelter. We were sitting in the control shelter. And keep in mind, we're flowing copious quantities of gaseous nitrogen through the system right outside our door. We actually all have our little O2 monitors there because it's a lot of nitrogen, oxygen depleting. And we hear this very large explosion. It's like 1 in, and we're like, okay. We need to draw straws to see who goes outside and figure out what's going on. I don't know. Because our cameras, we used our cameras and we didn't see anything, but we didn't have cameras inside the air handling unit. And my husband, he wasn't my husband at the time, but he volunteered. He was like, okay, I'm going to go. He takes his O2 meter, and we're like looking out the window. He comes back, and he says, well, I found out what blew out, and it was a manual damp valve, and it just blew out the side of an air duct. So we regrouped, and we, of course, called our bosses and told them that we weren't going to be done on time. And so then we regrouped, and they called in some independent folks and said, okay, what's wrong with the system, or what's wrong with these people? Luckily, they said, well, the system is the problem, and the A&E firm did all the right things. If they were looking at every single little piece, said, yeah, this valve and these pipes will take it from 5,500 to 2,700, and yeah, this valve will go from 2,700 to 180, and et cetera, et cetera, et cetera. But you put the whole system together, and it's not going to work. And, you know, there is not enough of, basically there's a lack of an accumulation effect there. There was too tight of a system, and everything was too reactive to each other. There was no way to dampen out the turbulent effects of the flow. And the A&E firm did not use any kind of modeling and simulation or anything like that. So we redesigned the system to where we put in lines, and we actually put in accumulator tanks, which actually allowed the system and kind of dampened out the response and allowed that system to ease up a little bit, and those PID loops weren't reacting with each other and overreacting. So eventually we did get the system working. But at that time, you know, that's when as a young engineer, you know, I learned two lessons. One, never inhibit your relief system. You know, but you know, they're there for a reason, and they're not controlled. They shouldn't be controlled. And but certainly the importance of simulation and modeling and systems integration, and you know, really looking at how the system works together and not just designing each piece at a time. So that was a very very important lesson for me. So that was my systems engineering lesson as a systems engineer. So I left the Cape, went to Huntsville, became a program manager, walked into a program, and they said, hey, we're glad you're here. Our program's behind schedule, and it's red, and it's over on cost, and good luck. So I said, all right, so, and now I'm going to kind of speak in generalities. I'm not going to talk the specifics of the program or the requirements, but I'll speak in generalities of what was going on. So we had systems engineering, but the team was kind of scattered and not focused and didn't have all the right relationships with the customer, because not only is engineering approach needed for a technical complexity and a business need, but relationships with customers is very, very important as well, and I think that really comes from the systems engineering team, and that was one of the things that was missing in the beginning here. So So my first 30 days there, we did a review, and I'm like, okay, what's going on? Well, they were actually heading towards their third SRR. And I'm like, okay, well, what was wrong with the first two SRRs, you know? I mean, that was part of the problem. You're supposed to have one, and they were on their third one. So when I said, well, the customer is crazy, right? They want to take one product, but they want it to do 5 things that physically are impossible. They want to break the laws of physics with this one product, and you know, they want to pay for one thing, and they want it to do something that 5 separate things used to do, basically. And part of it is, you know, there's laws of physics that they can't combine, and they don't get that. So, you know, so we had that problem. So we delayed the SRR. We got some key systems engineering players involved, good communication skills, relationships with customers. We were in the do loop, but if those were the customer requirements, the first SRR looked like that. They said, okay, we can meet these requirements. You know, as good systems engineers, okay, I'll just take a chunk out of the middle. That must cover the middle and must be good. Well, no, that wasn't good. So the second SRR came along, I'll just make it a little bit bigger. I can squeeze out a little bit more. Like customers like, no, that's not good. So the third one, this is about the time I stepped in and said, okay, well, let's talk to the customer and say, what, of these 5 requirements, which ones are really important to you, because there's these laws of physics and we can't combine all of them. You know, some of them clash. And so they said, well, we really care about the high-end requirement. And we said, oh, well, we can meet that, but, do you have an alternate solution for the bottom end? And the customer says, yeah, we can do that. So our do loop ended, but again, it goes back to a good relationship, good understanding of the requirements of the user and the customer, and we had a successful SRR. We were still behind on schedule, and we were still overrun on cost, but the same systems engineers for the life cycle of the program, as I said earlier, never get rid of your engineers. Your systems engineers, they're with you for the life cycle of the program, because when we started building product, now these over here, I just use these as an example. I grabbed these from that NASA website because I'm going to talk about mass properties. The product we were building, we had to verify our mass properties, and the contract wanted us to verify every single one. Well, that was driving cost and schedule. So the systems engineers team that we put together, they said, well, our build is repeatable, our performance is great, our tolerance is tight. Let me work with the customer, and maybe we can eliminate some of that verification and pull the pure performance to the left, and maybe we can gain back some of our schedule and reduce some of our costs. So that's what they did. We were all very supportive of the systems engineering team. They did their analysis, partnered with the customer, and that's why your systems engineers need to stay for the life cycle of the program all the way through verification, because not only do you want to make sure you meet your requirements, and sort of the customer does too, but all along the way there's optimization that can be gained as well.
And I had a similar, or was part of the tail end of a similar experience when the F-22 program was coming out of EMD, and there were some of us who had been on the program, and I was one of the short-timers in some regards back then, had been on the program for 15 years and had that kind of relationship. So when it came down to the verification, there was a very rapid narrowing to the really key parameters.
Yes.
And the other ones, and there were some of the other ones that weren't as important, and it was, okay, you did a test, it looks reasonable, you've been really good on all the hard ones, we have trust, you've shown me the data, I'm happy, check it off. The same kind of process.
It really is. The life cycle of the program, it's a benefit when you really engage the team the whole way through. Yep. Okay, so we can live without systems engineering, but why would you? At what cost, right? So the examples I've shown, if we did not have or embark on this journey with systems engineering, Bell Labs would have probably been slower to communicate across the world. We might have lost the space race to the moon, because their evidence shows if we did not stick with the Saturn and use the lunar module as our means to go to the moon and back, we probably would have missed that decade. Technical risk is high. Cost is high, longer to make products. But personal life. So I was thinking about what life would be like without systems engineering, as my husband is adjusting the spa using his iPhone. He's turning on lights in the pool using his iPhone. And the refrigerator is making our Keurig K-Cup coffee. And why we needed that, I have no idea, but he thought that was cool. He's a retired Lockheed Martin director too, so he's like, okay, we need that refrigerator with the K-Cup coffee in it. Talks to Alexis all the time. My dog's trying to figure out who Alexis is, but talk to Alexis now to find out the weather. We don't have to turn on the TV. And my car, I was so long that my car drives itself. I have an Acura and it actually drives itself. So, I just can't imagine what life would be like without systems engineering. So I'm not willing to let go of it. I did find the DAU report talks about tailoring of the process, and that is certainly an option because there are some simple programs that, you want to tailor it, but it's all about the risk. It's all about the risk and uncertainty and complexity. So we all got to be cognizant of that and how we tailor it to make sure that we're not taking undue risk. It needs to be proportional based on the complexity, maturity, and the risk of the project. So thanks to Bell Labs, the Department of Defense, and NASA for getting us started on this journey. Because without it, programs would fail, and our future would not progress as we've seen it in the last century. So now I have a problem in a call. I was part of a problem last Thursday, and I have a call to all systems engineers. So Thursday night, I was here working late. Mom keeps me working late here. We work after 7. I go out to my car in the back, and I have a flat tire, and I'm like, oh my God, it's a flat tire. So, Firestone closed and all that, but anyway, I decided to leave my car here, and I got to ride home. But my call to all systems engineers is to invent this so I no longer have to worry about my tires.
Doc, we better back up. We don't have enough roads to get up to 88. Roads? Where we're going, we don't need roads.
Sober mode. Sober mode like that. All right.
You guys would just work on that? No more tires. So that is it. So you have any questions for me?
I think okay.